Alright, implicit differentiation. So implicit differentiation is a technique that's going to allow us to take a derivative without explicitly solving for y. So this is really handy because you can't always isolate one of the variables. Up until this point, we've been talking about functions that are of the form y equals f of x. Okay, so here we have the y's on the left and the x's on the right. It's not always the easiest thing to do to separate the variables like that. So for cases like that, that's why we have implicit differentiation. So let's see an example of this in play. So suppose we want to determine the equation of the line tangent to the curve at the given point, and our function is x to the fourth minus x squared times y plus y to the fourth equals 1, and the point that we're looking at is negative 1, 1. So let me just sketch what this looks like. Okay, it kind of has a roughly trapezoidal shape, and we are interested in finding the equation of the tangent line at the point minus 1, 1. Okay, so that's the goal of this problem. So in order to determine the equation of the line tangent to the curve at the given point, we really need to know the slope of that line. The only way we're going to be able to find the slope of that line is if we find dy dx. Okay, so we're going to take the derivative with respect to x of our function here. Alright, so implicit differentiation, when we have y's and x's, typically we're going to be taking the derivative with respect to x, and we're assuming that y depends implicitly on x. Okay, so if we're taking the derivative of this whole equation with respect to x, we can treat the x terms like usual. So this first term, we have x to the fourth. The derivative of x to the fourth is 4x cubed. And then we see the middle term is minus x squared times y. We're going to have to use the product rule here. So we have minus the quantity, and now we have the first, x squared, times the derivative of y. So remember, y implicitly depends on x. So the derivative of y we write as dy dx. Some people write it as y prime. Okay? Either notation is fine. So we have x squared times dy dx plus y times the derivative of x squared, and we just differentiate that like normal. Okay, so that takes care of the middle term. And then lastly, we have plus y to the fourth, so we can use the chain rule here. So we have plus 4y cubed, but then we have to multiply by the derivative of y, which is again dy dx. Okay, so that takes care of the left-hand side. Then we've got equals 1. It's just a constant. The derivative of 1 is 0. Okay, so in my opinion, the hard part's over. Now it's a matter of solving for dy dx. So let's see. Let's clean things up a little bit. I'm going to distribute the negative through. So I've got 4x cubed minus x squared dy dx minus 2xy plus 4y cubed dy dx equals 0. Okay. Now I'm going to gather the like terms. So I'm going to gather everything that has a dy dx in it, or at least I'm going to keep that on the left-hand side, and I'm going to move the 4x cubed and the minus 2xy over to the right-hand side. So let me flip to the next page to do that. So we will have minus x squared dy dx plus 4y cubed dy dx is equal to 2xy minus 4x cubed. Now we can factor out a dy dx, and we have dy dx of 4y cubed minus x squared equal to 2xy minus 4x cubed. And lastly, we can just divide out by the 4y cubed minus x squared term, and we will have found dy dx without ever needing to explicitly solve for y. So dy dx is equal to 2xy minus 4x cubed over 4y cubed minus x squared. Okay, so the problem had asked us to find the equation of the line tangent to the curve at negative 1, 1. So that means we need the slope at negative 1, 1. Therefore, I'm going to evaluate this derivative at negative 1, 1. And so when we do that, we plug in negative 1 for x, 1 for y. So it's a little different than evaluating the derivatives we've seen before at a specific point. Now we're evaluating at an x and a y coordinate. Alright, so we've got 2 times negative 1 times 1 minus 4 times negative 1 cubed all over 4 times 1 cubed minus negative 1 squared. When all is said and done, that comes out to be 2/3. So the slope at negative 1, 1 is 2/3. To find the equation of the tangent line, we can use the point slope formula, which is y minus y1 equal to m times x minus x1. So in our case, we've got y minus 1 equal to 2/3 times x minus a minus 1. And so once we solve that for y and put it into mx plus b form, we get y equal to 2/3 x plus 5/3. And that's how that one would be approached. Let's see one more example. Okay, so now suppose we want to find the second derivative, and we have to use implicit differentiation. How do we approach that? So here we want to find the second derivative of e to the 2y plus x equal to y. Okay, so let's start by just finding the first derivative. So I'm going to take the derivative of the whole equation with respect to x. So the first term is e to the 2y. So the derivative of e to the 2y is e to the 2y, and then we apply the chain rule. So we have e to the 2y times the derivative of its exponent, 2y, which is 2 dy dx. And then we have plus the derivative of x, which is 1, and that's equal to dy dx. Okay, so now we want to again gather all the terms with the dy dx so that we can ultimately solve for dy dx. So I'm going to subtract dy dx from each side, and I'm going to subtract 1. And that's going to give me 2e to the 2y dy dx minus dy dx is equal to minus 1. We can again factor out a dy dx, and we would have 2e to the 2y minus 1 is equal to minus 1. And we can again divide by that quantity to solve for dy dx. So dy dx is going to equal 1 over 1 minus 2e to the 2y. Where I did a little simplification in my final answer here, it would have originally been minus 1 over 2e to the 2y minus 1, and I just factored out a negative 1 to cancel with the numerator. Alright, so that's dy dx. Now, to find the second derivative, we take the derivative with respect to x of this dy dx that we just found. So let's see, what would that look like? So we've got d dx of our dy dx. So we can write that as d dx of 1 over 1 minus 2e to the 2y. Oops, let me rewrite that, it's a little messy. So you might be thinking, well, there's no x's in what we're trying to take the derivative with respect to x to. But we need to remember that y implicitly depends on x here. Okay, we're using implicit differentiation. So how would that go? Well, we've got a fraction, so we might as well use the quotient rule. So we've got the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. Now, the derivative of 1 is 0. The derivative of this minus 2e to the 2y term gives us minus 2e to the 2y times the derivative of 2y, which is 2 dy dx. Okay, so an application of the chain rule, all over 1 minus 2e to the 2y, the quantity squared. So let's simplify that. That's going to give us 4e to the 2y dy dx all over 1 minus 2e to the 2y quantity squared. And we don't want to leave our answer with a dy dx in it, but from the previous page, we know that dy dx is 1 over 1 minus 2e to the 2y. So let's just plug in 1 over 1 minus 2 to the, 1 over 1 minus 2e to the 2y into our solution, and we'll have our final answer for the second derivative, which is 4e to the 2y times this 1 over 1 minus 2e to the 2y all over 1 minus 2e to the 2y, the quantity squared. And we can make it look a little nicer and write it as 4 times e to the 2y divided by this whole quantity cubed. Okay, so have fun playing around with implicit differentiation. It's a really cool tool to use, and I'll talk to you all later.